Okay, first one up here. What do we got for what constitutes an Arrhenius acid-base theory? What's an acid? That sound good? When something's added to water and the hydrogen ion concentration goes up, that something is an acid. Good? And then it's the almost exactly the same thing, right, for the base? Why is it important that we're saying when something is added? Okay, but ultimately what we're saying is I don't actually have to put H pluses into the water, and I don't have to put OH minuses into the water for water to all of a sudden have more H pluses and OH minuses. Because the water itself could be the source of the H plus or the OH minus. What about the Bronsted-Lowry acids? They specifically say proton. And then the base. Okay, how about our Lewis acid base? What's the acid do? What's wrong with the Arrhenius theory? I'm sorry, something, what?
It just has to do with water.
Okay, one problem is it's a very specific must be talking about it being in water. And not all acid-base reactions happen in water. What else we got? Okay, H pluses do not exist free in water. You'll have a hydronium ion. What else? Oh yeah. We don't actually need H pluses or hydronium ions at all. That's not a requirement for something to be considered an acid or a base. And he had water separating into hydrogen ion and hydroxide ion with no energy input. Okay, what about Lewis naming nitrogens as Lewis bases? What is it that's important about the nitrogen? No. What's my Lewis structure for a nitrogen atom? An N with what? How many dots? 5. And then the nitrogens, based on their position on the table, typically make how many covalent bonds? 3. So then if I have a bond going off in this direction, and a bond going off in that direction, and a bond going off in that direction, what do I have here? A lone pair of electrons. So these lone pair of electrons this is phenomenally important for biological systems. When we think about bases, we think about the hydroxide ion. There isn't a whole heck of a lot of hydroxide running around inside of your body, but there are zillions of molecules with nitrogens on them. So the nitrogen is actually the base that your body uses for acid-base reactions almost always. Yeah, that's fine. The acetic acid, so I've got HCHH, C double bond OOH, and then the condensed structural formula is CH3, COOH. What I asked you to do? Which one of these is acidic? Draw the structure below. Also write okay, so which one of these ones is the acidic one? So there's 2 ways to figure this out. One, if one of them is different than the other, that's probably the one we're talking about. So the other 3 are just connected to a carbon, and I wouldn't be able to tell them apart from each other. But that one on the far side is connected to an oxygen, so that's one way. Remember when we were talking about polyprotic atoms? We had the phosphoric acid and the phosphorus acid, and the phosphoric was a triprotic, and the phosphorus was a diprotic. Why did that third H on the phosphorus acid, why is it not an acidic hydrogen? What was the requirement? Hydrogen bonded to an oxygen. And one of the hydrogens on the phosphorus acid is bonded directly to the phosphorus and not to an oxygen in between there. So it makes it less likely. What's super important about this hydrogen-oxygen bond? It's super polar, not just polar, but really negative here and really positive here. So what that does is, since this thing looks really positive, then something can come over that's negative and snatch it off of there, like a water molecule. So if a water molecule shows up, this partially positive hydrogen can attach itself to one of those lone pairs, because the lone pairs are a Lewis acid, and then I get this thing leaving as an H3O plus, and I have an acetate polyatomic ion behind. So why are these guys not considered acidic? Yeah, they don't have much of a charge, right? Because this is 2.1 and this is 2.5 for the electronegativity. So that is not polar. So because there's no positiveness on that hydrogen, nothing negative is going to come over and grab hold of it. Actually, what happens when something that's got a charge comes in contact with a hydrogen that's bonded to a carbon? So since this difference in electronegativity is small, this part of the molecule appears what? It appears nonpolar. So a water molecule would completely shy away from that side. Instead of yanking an H off, it would say, no, I don't want anything to do with that. Okay, how are we going to make a 2-molar hydrochloric acid solution starting with concentrated hydrochloric acid? So you need to know what? should have looked through the notes or are online to find out what piece of information. Nope. That the concentrated hydrochloric acid's molarity is 12.1 molar. Or if you use 12, that's fine. So once I know that, what equation do I use? The dilution equation. So I have this concentrated acid, and I want a less concentrated acid. I'm going to dilute it down. I know that I want to make 2 molar hydrochloric acid, and I know I want to make 750 milliliters of it. And I know I've got 12.1 molar concentrated stuff to work with. What I don't know is how much of the concentrated do I need? So, what is that? 1, 2, 4 milliliters. Okay, so describing exactly how I'm going to make this, I'm going to add 124 milliliters of con HCl to a 750 milliliter vol flask. Add water near line, add water to line with a dropper. I think I erased that. Stupid. So I know in this solution that the H plus ion concentration is 2.59 times 10 to the minus fifth. I want to know what the pH, OH concentration, and POH are. So what's the pH going to be near? 5. And then which direction is it going to go because it's not 1 but 2.59? It's more acidic, right? So the number's going to go down. So my number had better be something for something or other. So negative log 2.59 E negative 5, close. Okay, so I have a pH equal to 4.59. And so then I have a POH equal to 9.41. And so that means I have a hydrogen ion concentration equal to 10 to the negative 9.41. Or, if you prefer, you could say 3.86 times 10 to the negative 10th molar. Either of those are fine. Just log. I take the log of the value and then multiply by negative 1. So if I take I will get that 5.9 number, 4.59. So I got a pH of 2.36, hydrogen ion, hydroxide ion, and POH. So my hydrogen ion concentration, so we 10 to negative 2.36, and my hydroxide ion concentration, and my POH, 11.64, 10 to the negative 11.64. Is that right? 13, 14? Yeah. Are we good with those? Again, if those decimal placed exponents irritate you, you can just punch in like 10 to the negative 2.36 and you'll get a something times 10 to the negative third number. So I've got 0.2 molar hydrochloric acid, and I want to know what the pH is. So negative log 0.2. I'll just say 0.7 since I only have one decimal place here. Seriously? You're not letting me undo it? So the pH in this case would be 0.7. How come it's okay for me to just take the negative log of the hydrochloric acid concentration? What's important to realize? It's a strong acid. So up here it was okay for me to do what I was doing because I was telling you flat out what the H plus ion concentration are and what the pH are. And down here I'm telling you what the hydrochloric acid concentration is, but in reality, since the HCl is a strong acid, all the H's and Cl's have already been separated out. So if I've got 0.2 HCl, I've got 0.2 H plus, and I have 0.2 Cl minus. I don't know why I can't get rid of these stray lines. They're irritating me. Okay, so how about the second one? Or the next one? How's it different? If I just go ahead and take the negative log here of the 0.2, I'm obviously going to get the same number, 0.7. But what did I take the negative log of? Of the OH. So this is not pH I calculated. This is POH. So then it's going to be 13.3 is my pH. So when you're looking at these problems, it's fine to take the negative log. You just got to realize what it is that you're taking the negative log of. Is it the acid or is it the base? And then you can adjust accordingly. Okay, how about this cartoon? It's only partially true. What? Why did they recommend it at one point? What? What comes out? What's the pH of the urine? Acidic or basic? Yeah, I don't know why you're saying ammonia, because it's uric acid that's the major concentrate. So what would you expect these tentacles, what kind of substance must be being placed on the person? A base. So the idea was that these jellyfish would hit somebody and they would inject them with a poison that was basic. So if you peed on the person, then it would neutralize the base and then everything would be fine. And that'd be great if all jellyfish injected you with basic stuff, but it turns out it's pretty close to 50-50 whether you get injected with a base or injected with an acid. So if you get injected, like your foot gets hit and you have acidic poison all over your foot and then you pee on it, what's that going to do? That's going to make it worse. So that's why it's like no longer recommended. Sure, but I probably just dump water on it in that case, since I'm probably next to an ocean, possibly. I guess if you had one of these things in your freshwater tank at your house, seeing that some of them are like 100 feet long, that'd probably be problematic. How about inside this little box? What do you got? Everybody should probably have said what? That's stomach acid, right? Don't want to get thrown up on by anybody, not just because it's gross, but because it could hurt. Anything else? What else we got? Great. Uric acid. What else? That's it? All you found was P and hydrochloric acid? What? deoxynucleic acid. Okay, so the A in DNA. So the ribonucleic acid, it is acidic. It's a pretty big molecule, but for certain. Something else? Nobody wants to say lysine, glycine, any of the amino acids? All your proteins are amino acids. Any of your amino acids would have been fine. How about anything that constitutes a cell membrane? Those guys are all fatty acids. Arachidonic acid? No? Okay.